So in this video, we're going to look at another example involving a confidence interval for a proportion. A December 2018 Hill-Harris-X poll asked 1,001 randomly selected adult Americans, quote, "Do you believe the results from political polls that are reported in the media?" End quote. Of those asked, 191 responded, "Almost never." Determine a 90% confidence interval for the proportion of adult Americans who almost never believe the results from political polls that are reported in the media. Determine a 95% confidence interval for the proportion of adult Americans who almost never believe the results from political polls that are reported in the media. What is the impact of increasing the level of confidence on the margin of error? So in this example, what we're doing is the same thing sort of twice. We're going to do a 90% confidence interval, and then we're going to do a 95% confidence interval. And the point of the example is to see what's the difference. Well, so we're going to do this on a separate sheet. So, part A, first of all, let's write down what we know. We were told that there was a poll of 1,001 adult Americans, and of those, 191 almost never believe political polls that are reported in the media. So in part A, we want to find a 90% confidence interval. In part B, we want to find a 95% confidence interval. So the work will be essentially the same with just a difference in what the critical value is. So again, I'm going to do both of these by hand, and then we'll talk later about how to do these on the calculator and in StatCrunch. So if I'm going to do this by hand, the first thing that I have to do is find my point estimate. The point estimate is going to be the same for part A and part B. So point estimate is going to be p hat, and so that's going to equal 191 out of 1,001. So if I take 191 divided by 1,001, that is 0.1908, so about 19%. So about 19% of adult Americans almost never believe political polls that are reported in the media. So now we know that our sample size is 1,001, and we know that p hat is 0.1908. So we need to make sure that our conditions are satisfied for constructing a confidence interval. So we need to check, is n times p hat times 1 minus p hat 10 or bigger, and is n less than 5% of the size of the population? Well, again, we know that n is 1,001, so if we take 1,001 times p hat, which is 0.1908, times 1 minus 0.1908, we're checking to see, is that 10 or bigger? Well, 1,001 times 0.1908 times 1 minus 0.1908 is 154.55 if I round to two places. 154.55 is certainly bigger than 10, so we satisfy that condition. The other condition, we need to make sure that our sample size is less than 5% of the population. That's pretty obvious because our sample size is only 1,001, and certainly that's less than 5% of the population of adult Americans. Just to put a little more firmness on that though, if n is 1,001, then that needs to be less than 0.05 times the size of the population. If we divide both sides by 0.05, then taking 1001 divided by 0.05 is 20,020. So 20,020 is less than or equal to the population size. So in other words, as long as our population is larger than 20,020, then we satisfy the condition that our sample size is less than 5% of the population. Well, again, clearly the population of adult Americans is larger than 20,020, so our condition's satisfied. So now we know that the conditions for constructing a confidence interval are satisfied. We have the point estimate, so now we need to calculate the margin of error. So to calculate our margin of error, that's going to equal z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. So we've got to figure out what our z value is for 90% confidence. So I have my normal distribution here. Here's 0. So there's going to be a negative z and a positive z, and I want this area in the middle to be 90%. So that means the area out in the tails is going to be the other 10%. And so half of that 10% is going to go in this tail, and half of that 10% is going to go in this tail. So half of 10% is 5%. So the area in this tail is 0.05, and the area in this tail is 0.05. So I need to figure out what are the z-scores that's going to give me this area of 0.05 in the two tails. So again, I can figure that out using the standard normal table. So if I bring in the negative side of the table, I will be looking for 0.0500 here in the table. So here is 0.0505 and here is 0.0495. So 0.0500 would be right perfectly in between those two values. Well, this value matches up with negative 1.64, and this value matches up with negative 1.65. So when we are perfectly in the middle, remember we split the difference. So 1.64, 1.65, if we average that, we'll get 1.645. So this critical value right here is negative 1.645, and by symmetry, this is positive 1.645. And just for the sake of it, if I'm using 90% confidence, 1.645 will be the critical value. Now, so that's going to be my z sub alpha over 2 here. So 1.645 times the square root of 0.1908, that is the p hat, times 1 minus 0.1908, that's 1 minus p hat, over n, which is 1001. So if I bring back in my calculator, 1.645 times the square root of 0.1908 times 1 minus 0.1908, close parenthesis, divided by 1001, that is 0.0204. So this is 0.0204. So my 90% confidence interval is going to be 0.1908 minus the margin of error, 0.0204, to 0.1908 plus 0.0204. So if I do those calculations, 0.1908 minus 0.0204, that is 0.1704. So this is 0.1704. And if I take 0.1908 plus 0.0204, that is 0.2112. So 0.2112. So I'm 90% confident that the true proportion of Americans who almost never believe political polls that are reported in the media is somewhere between 0.1704 and 0.2112. Now in part B, we're repeating the same problem, except we're going to be using 95% confidence. So the only thing that's going to change, my point estimate's going to be the same, my formula is going to be the same, but this value is going to change because I'm using 95% confidence. So if my confidence level is 95%, then that means this area between negative z and positive z, this area is going to be 0.95, which means this area out in the tails is going to be, the total is going to be the other 0.05, half of it in each tail. So this area here is going to be half of 0.05, which is 0.025, and this is also 0.025. So again, I can look that up in my normal table. We did that in the previous example. 0.025, that gives us negative 1.96 as the left critical value here. So this is negative 1.96, which by symmetry means this is positive 1.96. And again, we could have also looked that up right here. 0.95, so that is 1.96 for the critical value. So my margin of error, if I'm using 95% confidence, is going to be 1.96 times the square root of 0.1908 times 1 minus 0.1908 over 1001. If I bring my calculator in, 1.96 times the square root of 0.1908 times 1 minus 0.1908 divided by 1001, that is 0.0243. So this is approximately 0.0243. So my confidence interval is going to be 0.1908, my point estimate, minus 0.0243 to 0.1908 plus 0.0243. So if we do those calculations, 0.1908 minus 0.0243, that is 0.1665, and 0.1908 plus 0.0243, that is 0.2151. So 0.1665 to 0.2151 is the confidence interval. So if we use 90% level of confidence, our confidence interval is 0.1704 to 0.2112. If we use 95% confidence, then our confidence interval is 0.1665 to 0.2151. So question C is, what is the impact of increasing the level of confidence on the margin of error? So if we increase the level of confidence, so we went from 90% confidence to 95% confidence, what happened to our confidence interval? Well, if you look, our margin of error went up. It went up from 0.0204 to 0.0243. So a higher level of confidence caused a larger margin of error. And so the result of that is we went from a narrower confidence interval to a wider confidence interval. So increasing the level of confidence increases the width of our confidence interval. So if we want to have a narrower confidence interval, then we can reduce the level of confidence. But if we want to have higher confidence, the trade-off for that is that we get a wider interval. And hopefully that makes sense. We could be, say, 80% confident that the parameter is in here, but to be more confident, so if we want to be 90% confident, it's going to take a wider interval. To be a 95% confident, it's going to take a wider interval. To be 99% confident, it's going to be a wider interval. And so that's the trade-off that I was talking about in an earlier video. Why not always just use like 99% confidence? Well, the 99% confidence, we can do that, but it makes the interval wider. So there's a trade-off. And so that's sort of the point of this problem. So the answer, incidentally, to part C, what's the impact of increasing the level of confidence on the margin of error? We end up with a larger margin of error. So the answer to part C, we end up with a larger margin of error when we increase the confidence. And that also then means we have a wider confidence interval. So next we're going to look at how we can find confidence intervals using technology.